Okay, so he was interested in the shape of celestial bodies, so the sun, the planets. You're basically modeling self-gravitation with surface tension. Okay, so rotating heavenly bodies. You have a rotation axis, and there's self-gravitation, right? So it's self-gravitation wants to keep things spherical to minimize the gravitational potential energy, and rotation is giving rise to a pressure which causes it to bulge. Okay? So that's gravity, and then you have rotation, which is going to tend to flatten it out. And this, he realized, can be modeled, the role of gravity there can be modeled by surface tension. So surface tension also wants to keep things spherical to minimize the surface energy in the system. Okay. By this stage, by the way, Plateau had lost his eyes by staring at through the new telescopes, and so he had his son-in-law help him in the lab. And so what he did is he basically took a wire and he put an oil drop on it, so the oil drop was neutrally buoyant in water, so there's no gravity in the system. And then he spun the wire, and he looked to see how the shape deformed as the rotation rate increased. Okay. So he basically looked at this as a model of this. Okay, and there's an account of this given. There's a whole book because of the astrophysical applications of this. Ellipsoidal bodies of revolution. And this is a book by Chandrasekhar, who's one of the few fluid mechanicians to have won a Nobel Prize. This is a very nice book. And it turns out so the progression of shapes you get is the same in these two systems. Okay, so as you increase the rotation, you go, we'll see in a minute, we'll actually solve the problem, but it goes oblate ellipsoid, then it actually breaks symmetry, and you get these hot dog shapes, and then they'll eventually break. Okay, so, and this, so there are two other applications. So the one is the geophysical. Okay, so it's obvious to us now, but it wasn't obvious to people then, at the time of Newton, whether the Earth was going to be oblate, so like this, it's going to deflect in this fashion in response to rotation. And this is what was predicted by the Cassinis, and Newton predicted that it would be oblate. Okay, so this is a time when there was a great competition between the English and the French in terms of taking precedence for development of calculus and so on and so forth. And of course, Newton was heavily involved in much of the controversy. So this was settled actually by Maupertuis. So Maupertuis was a French scientist, and he went to Lapland. So he went up north and took geodetic measurements, and so he was able, from which basically give an idea of the shape of the Earth, and so he was able to confirm Newton's predictions that the Earth was oblate. And I thought it's funny. I just read something over the Christmas which informed this. So Voltaire initially applauded applauded Maupertuis for having hammered down the Poles and the Cassinis, which is a good line. Voltaire had all sorts of good lines. But then Voltaire suddenly turned on Maupertuis and then started mocking him, saying, you have to go up north and do all this stuff just to prove what Newton could do at his desk, right? And so, but it turns out that Maupertuis, when Maupertuis was up in Lapland making these measurements, Voltaire stole his girlfriend. So his girlfriend being Émilie du Châtelet. I just discovered that over. So now it makes sense. I go, what? Why would he say something so nice and then something so nasty? Cherchez la femme, as they say in France. Okay. Okay, so let's try and. Okay, so another application of this. Of this problem is the rotating drop tensiometer. Okay, so we imagine we have a cylinder of fluid and we're going to rotate it around its long axis. Okay, so if we put a blob of light fluid in this is heavy fluid, this is light fluid, what is it going to do in response to rotation? We know that in a rotating frame, if our room is rotating, we get thrown out towards the wall, but if we're holding a buoyant balloon, it goes in towards the middle, right? So, yeah.
So the light fluid.
This is the light one. It's going to go along the axis, right? Because all the heavy fluid is thrown outwards. So this thing is going to distort like this. Okay, we're going to solve this problem today. And when you do that, you can find, so again, you have rotational effects causing it to be pulled out along the axis, and surface tension is resisting it. And so from the length of the bubble, it turns out in the high rotation limit, it basically goes out into a cylinder with spherical caps for the same reason that a puddle goes flat and then has just localized regions of curvature. And so from the length of this, you can actually infer the surface tension. Okay, so maybe I should do it slightly better. So this is rho minus delta rho. Rotation, okay, and so from the gives surface tension. So this was actually the PhD work of Vonnegut, so he's actually a professor at MIT, and his brother is Kurt Vonnegut. If you've ever read, yeah, he's a well-known novelist. He wrote that's Kerouac. But what he wrote, the one about Slaughterhouse 5. But he in one of his novels, he talks about his older brother, who's this guy, who's a scientist, and he said he always envied his brother because his brother actually enjoyed his work. I think that he was a sort of a tortured writer. Okay, so we want to now pose this problem formally. Okay, so this rotating, we want to be able to consider the case where the drop is heavier or lighter than the external fluid. And so basically, it's going to look like this. So let's develop this. Maybe I'll do the extended. Okay, so we have our drop rotating about a vertical axis. We have density outside. For the sake of argument, we'll take this to be positive, so it'll be positive, but we can switch the sign as we like in terms of the density anomaly. And we're going to, so we have a surface S here. This is bound by surface tension, sigma. We have a unit normal N. And we can describe the height. So if it's axisymmetric shape, then we can, this shape is uniquely prescribed as a function of R. Okay, so the pressure on axis, so the center is going to be P naught plus delta P. And we expect the pressure to increase with R squared, so the centripetal pressure. So the normal stress balance so we have the curvature pressure balancing. The dynamic pressure, so the whole system is rotating. So it's only the density difference that contributes to the centripetal pressure difference. Okay, so we non-dimensionalize. Okay, this is prime, just indicating that it's a dimensionless gradient operator. Okay, and delta P primed, A delta P over sigma. And this variable here, so we've seen a bond number is gravity to surface tension. This is going to be a rotational bond number. So this is a measure of the characteristic centripetal centrifugal force to curvature. Okay, so that's the rotational bond number. Okay, so we can evaluate the normal and the divergence of the normal if the shape is truly axisymmetric. We're going to see that that only holds up to a certain point, and then you get a symmetry breaking instability. So for axisymmetric shapes, okay, so our normal, as we saw before, is the gradient, the surface functional, divided by its magnitude. And so the divergence of the normal Okay, so one can actually integrate this if you so this is basically our governing equation here. And by changing the sign, so by making the fluid heavier or lighter, relative to the ambient, you can change the sign of the rotational bond number. So then we have the surface tensiometer geometry, where we have a light drop spinning in a heavy fluid. And again, so drop length can be used to do sigma. We'll actually solve that in a moment. And it's particularly useful. So for very high rotation rates, this goes into a cylinder with spherical caps. Okay, so Brown and Scriven looked at this problem. This is where these curves are coming from. And what you're seeing, so when bond number equals 0, there's no rotation. As we increase the rotation, the thing is becoming prolate. So this is the shape, this is the top quadrant of the drop. So it's basically getting flattened. And then as you rotate higher and higher and higher, the axisymmetric solution goes unstable. Okay? So you basically always have an axisymmetric solution here, then it goes unstable, and it basically goes into a lobe shape. And you can actually get solutions which are multiple lobes, but these don't seem to be observed experimentally. So Skip Scriven was a sort of giant of surface tension problems. Bob Brown was a professor at MIT. Okay, so for bond number so for weak rotation, you only get these axisymmetric solutions. For intermediate bond number, okay, so you can have stable solutions which are either these prolate oblate ellipsoids or these lobes. They basically look like, imagine a peanut, right? And then as the bond number increases further, okay, so that's effectively what we see here. We only get these lobate solutions as you crank the rotation rate up. So again, so this is the R max, so this is the maximum radius of deformation divided by the unperturbed radius of the drop. So as that increases, as the rotation increases, that does as well. So you basically get, when you're close to zero rotation, you basically have these spheres, then they distort, and here you can see axisymmetric biconcave forms, which actually look like this, and then you get these lobe-like solutions. So for small rotation, both are stable, so you have the possibility of two. So if you perturb the drop, it may jump from one to the other. And this is actually, so again, you get exactly the same forms for self-gravitating bodies, which is quite surprising. And then you have no stable solutions, but you can get these sort of.
Saying that there's gravitational bodies that look like this.
Yeah, so I think there might be actually. I don't know. I think there might be. Does anyone know?
Like what?
Gravitational bodies that are long and thin. I'm not really sure. Good question.
But John, I made a mistake. I missed something. How can you see these like peanut shapes? I mean, from this analysis, I'm not going to tell this, right? This
is for the axisymmetric. This is for the axisymmetric, right? Because we've had to. But then you have to. Then
very hard theoretically to get the peanut shape, right?
Yeah, you have to do a non-axisymmetric stability analysis.
But is that done or is like?
Yeah, these guys. Yeah, it's sort of numerical. It's kind of numerical. It's a mess. Yeah. Okay, so the same issues come up if you look at a dynamic problem. What's that?
To get the low form, you have to rotate faster.
Pardon me?
To get the low form, you have to rotate faster or what?
Well, you can see for a given rotation rate, all the information about the rotation rate is given in the bond number, so you can get either, right?
Okay.
So there are actually two possibilities.
So you said that you can choose one year depending on the perturbations of the system.
Yeah. So both are stable, right? And you can move from one to the other by giving it a kick. And those, by the way, these things are, these we made in the lab. I'll show you in a second how we did that. So if you look at, so you get the same shapes. You have rolling and tumbling drops. Okay, so these guys we made in the lab by rolling down, solder down hills. Okay, so we have so basically you have a drop running down a hill, and it's going to rotate as it goes. Okay, and it's basically going to rotate about its center point. Call this angle theta. Okay, so here we get similar shapes arising. Okay, so how do you actually get the rolling speed? You get it from energetics. So the rate of work done by gravity in pulling it downhill is going into dissipation. So that's the rate of work done by gravity. And so you have to calculate the amount of viscous dissipation. Okay, and so if this is actually wetting the surface, and there's a small region here, which is the dissipation zone. So this is a problem that Pamo and Mahadevan did. So you basically calculate, because it's in solid body rotation outside of that region, so there's no dissipation. So there's only dissipation in this region here. So you basically have to match a zero slip boundary onto the solid body rotation to get that boundary layer. So then you can then calculate the rate of dissipation, and that gives you then the rolling speed. And if you have the rolling speed, this gives you the rotation speed. Okay? And from the rotation speed and the surface tension, you get the shape basically from this.
What does tumbling mean here?
What is what?
Tumbling means it's rolling and...
So I'll show you. So if it goes into one of these low bait things and it actually starts tumbling.
Oh, tumbling, that's okay.
Yep.
Okay. Well, tumbling is just like it's rolling and a non-circular...
Yeah.
Just tumbling is rolling in a non-circular fashion?
Yeah. Rolling, if it's non-axisymmetric body, then it will tumble. Right? Okay. Okay, so the shape progression is the same. Here, it's probably better to show you. Tumbling is like an acrobat. Like an acrobat tumbles. After you score in football, you tumble, right? You do that. That's called tumbling as well. Right? That's what gymnasts do. Okay, so here's a drop rolling down a ramp and then taking off. So you're seeing it goes into this biconcave form. It's sort of in the lifesaver shape, but then it evolves into a peanut. Okay? And this is like a millimetric drop. This is water coated with lycopodium powder. These are experiments by David Carré.
This is the evolution of the drop.
Yeah, exactly. So it's flying through the air there.
It's in shots through the air.
Yeah, it's rolling off the end of you can see the ramp on the left, right? So it's basically, it looks like a lifesaver, and then it evolves.
It's falling, it's not rolling.
It's rolling. Now it's falling. It rolled off the end of a ramp, right? So when it was...
It's not that falling.
It was, yeah, until it came, until it fell off the edge. Right? So there it's rolling. It's basically rolling down the hill and then off a ramp and then flying through the air. But this indicates that the stability is different. So it actually, these biconcave forms, which are unstable in the pure rotation case, are stable if it's rolling. Okay, and so this is our experiment. So we had this is a rotating drum, and we put molten solder inside, and looked basically at their dynamics, and they would tumble and roll. What's that? Solder is for a soldering iron. It's a metal that becomes liquid if you heat it up.
Oh, okay.
So we had to keep this hot. So we had a really high power hair dryer, and so these are things that we made in the lab with this tumbling device. And so this is tumbling here. right on the top. You then have a non-axisymmetric form.
And it jumps a little bit, right?
Yeah. It'll actually take off, yeah. Okay, so
In the middle, when it's a low, or is it always a depression, or will it have something like this in the middle?
sorry.
In the low form, is it always a depression, or for example, it will have something like this?
It's typical. It's usually biconcave, so there's a depression in the middle. Yeah.
Is there any rotation when it divides?
Sorry.
It breaks into two.
Yeah. Right. Yeah. Eventually, if it go to high enough rotation, it will break. Yeah. So these because you can see that like the drop that went from a lifesaver into a peanut, it looked like it was stretching, and then it'll stretch and break. Right. So at high enough rotation, certainly it will break. Right.
So you have to get something like a capillary event to get it.
That's right. That's right. So there's basically a critical size at which rotation will break the thing. Yeah. Okay. So then so in terms of these rolling drops, we've seen the stability different from the pure rotation case. So these biconcave okay, and those are unstable in the pure rotation case. Okay, and so where do these shapes come up? We got interested in them because there's something called tektites that arise. So when there are meteorite impacts, there are these large chunks of meteor, and they come and hit the surface of the Earth, and they give rise to so-called tektites. So this is the Earth, and if we have a meteorite coming in, then there's basically it basically splashes down, and it kicks up, it basically liquefies the Earth, and then you have these chunks of silicates, molten metals flying through the air. And what you find is these chunks they're about this big, and they're typically shaped like this or that. Right? So they're oblate ellipsoids of these lobate forms, and they're liquid metal. Oh, sorry. Well, what we find, of course, are solid metal, and these are called tektites. Okay, so what we want to try and do is understand. So these are these guys, tektites. So basically, they're the ejecta from meteorite impacts. So we see them in Arizona. You see them in the shops. They sell these things. And we wanted to try and understand why they're as big as they are, because they're huge relative to raindrops, right? They're sort of 10 centimeters across. So up to 10 centimeters. Okay, so let's first ask why they're so large. So they're at least an order of magnitude larger than raindrops. Okay, so if you remember our raindrop scaling, we argued that they should be the capillary length in size, right? So it's the square root of sigma over delta rho. So these are liquid metals. Liquid metals have very high surface tension, right? However, the density cancels, right? Because the density of liquid metal is about 10 times that of water. So they actually cancel. So the capillary length should be the same for both. So that's not the answer, unfortunately. Okay, so that's not sufficient. Okay, so these so it's suggesting that these things are not equilibrium bodies of revolution. They're basically frozen in flight. They're basically flying through the air. They're stretching. They're about to break up, but then they freeze. Okay, so why would they freeze into these particular shapes? So why is their shape different from raindrops? Why are they not? Okay, so here we can get it. We can answer this one. Okay, so here, again, so the density is very high. So liquid metal is 10 times that of water. So we know that the shape of raindrops we argue that it's set by the aerodynamics. So the aerodynamic pressures are very important, right, for the raindrop. Whereas these liquid metals, because the density is so high, the internal pressures dominate. So if they're in a state of rotation, the rotational pressures are going to dominate the aerodynamic pressures outside. Okay? Right? Because the aerodynamic let me write this down. So because the characteristic dynamic pressure is rho u squared, right? So it's linearly proportional to rho. So the pressures of the air are going to be smaller by a factor of 10,000 for these liquid metals. So in particular, so if it's rotating, then the rho omega squared r squared is with rho based on the inside of the drop. So if this is rho, then rho omega squared r squared, this is r, is going to be much greater than rho a u squared, which is a characteristic dynamic pressure acting on the air, right? So this is going to dominate this. So if it's tumbling, that is going to be the largest pressure in the system, and that's what has to be balanced by surface tension. Okay, so in fact, the drop shape is set by its rotation. So imagine basically this meteorite hitting in these drops, flying through the air, and their rotational motion setting their shape. Then they're basically freezing into shape as they go. So they freeze not in equilibrium forms, but their shape reflects their rotation and is not affected to first order by the aerodynamic stresses. Okay, so let's solve the Vonnegut problem now. This is something that we can do quite cleanly.
Why do they have to rotate in the first place?
What's that?
Why do they have to rotate in the first place?
Why do they? They don't have to. They just tend to, right? If you just look at a high-speed video camera of a rock hitting a pond, you'll see drops tumbling through there. There's usually some element of torque. And the point is, if you have any even if you have just a small rotation, that will dominate the aerodynamic pressures if the fluid is very dense. It is conceivable that you not have any rotation, in which case you'll get a spherical drop, and this does happen, but typically when you see, if you hit a free surface, drops will be tumbling as they fly. CSI? Yeah, nice.
Thrown by the wind or just committed suicide, right? Because if it was thrown, usually it hits with the back, right?
Oh, yeah.
It hits with the front. Because of the
Wait, this is if you throw a body off a cliff into water?
No, for example, out of the window, someone
Okay.
pushes you. You just jump. It's different.
So how can they tell? Sorry, say it again?
If it hits with the back, probably it was thrown. Because you already...
Oh, yeah, right.
Something like that.
Oh, interesting. I'll keep that in mind.
You always tend to do this, right? Because the head is heavier, right? So eventually we'll do this. But if it is
Did you learn that on CSI? Or did you think it through? Okay, all right.
I
Yeah.
learned that.
Yeah.
I mean, it makes sense, right?
No, there are a lot of there's a very interesting thing about cats. You know, if there's a
Yeah, the falling of the cat.
yeah, you know, yeah. If you have there's a plot. It's rather disturbing data, but it's the fatality rate as a function of height. So they have data from people's in New York City whose cats have fallen out of their apartment buildings, and so
Data from that?
yeah. So it's, as you expect, it's like 0, and then it peaks, and then it goes down, and then it goes up. So this is the number of stories. Turn the camera off for some of this. Okay, number of stories, right? So this is how high you are in the building, right? And
It's a cat or cow?
this is, and so okay, so this is the fatality rate. Okay, so there's a peak around 3 stories, and then it goes flat for about like 5 to 12, and then it goes up again. So do you know why that is?
It probably has some type of flip.
Exactly. So this is how long it takes to flip. Okay, so this is so basically if they're just fall this distance, even if they land on their back, they'll be fine. But here they can die if they land on their back, and there's maybe a 50% chance of their landing on their back. Of course, but here they're able to land on their feet.
From nine stories up and
Yeah,
okay?
yeah. I'm not sure about the numbers exactly, but it's quite high. Like it's pretty.
It depends on what you have on below, right?
What's that?
Depends on what you have below the story.
Yeah, what they're landing on. Yeah.
Because maybe if they hit with if they land like this, I mean, they can be completely collapsed.
Yeah, right. That's called
Concrete.
telescoping. Yeah. Yeah, but then the fatality rate goes up, and eventually it's 100% if they fall from whatever 30. But so how do they turn around and I need $1.
That's definitely not a cow problem, right? Cow cannot sit, right?
No, this is actually very interesting. So biomechanics is a very interesting subject. Do you know that if you take a mouse,
You want a coin?
there's a no, I need $1. So there's a critical height. There's a critical size of animal below which it can fall from any height. So a mouse thrown from the top of the Empire State Building will land on its feet and just run away. Yeah, yeah.
Wow.
True. So a mouse will survive a fall from any height.
Mouse, huh?
No, not my mouse. Any mouse or any smaller animal. Of course, a cow will splat. But a mouse, and so how does a cat turn around in midair? Have you ever thought about that? It's got to conserve angular momentum, right? So it can't just go like that, right? I mean, if aerodynamic torques are enough, it can eventually, right? But the point is that it wants to do it quickly, so as to avoid this fate. Okay, so ready? So this is a cat, and these guys represent, the face represents its legs. So imagine the cat is like this, right? And it wants to land like this, okay? But it has to do that without violating conservation of angular momentum. So it can't just go like that, right? And it can't just go like that. So ready? Goes like this, right? It's just folding it like this. And then, right? That doesn't violate conservation of angular momentum either. And then, right? See that? Then boom. Right? And that's exactly what a cat does. Have you ever seen a cat turn around? Because it goes, right? Not bad. You got it? It's a good trick in bars.
Jerry Marsden, I think, studied this.
Yeah, he had that.
Jerry Marsden, it's mechanical studies of this.
Oh, really?
Yeah. Of the cat, a white cat can turn.
Orient himself? Yeah. Where were we? Good question. Good question. It got me very distracted there.
I like the cat noise of turning around. And how's it if it's a cow turning around?
They aren't so agile, which is they rarely survive falls from great heights. Let's take a little break here. So.